Welcome back to my channel and Merry Christmas. Today I want to talk about a data structure commonly seen in graphs called disjoint sets. Disjoint sets are also sometimes called union find due to its two operations, union and find. Sometimes people refer to disjoint sets as a data structure and union find as an algorithm. But today in my channel we're just going to refer to it as a data structure. What are disjoint sets? Disjoint set is a data structure that stores a collection of disjoint non-overlapping sets. It is usually seen in undirected graph problems to check if two vertices are connected. For instance, we can use a disjoint set to determine if two people share a common ancestor. There are two terminologies in disjoint sets, the parent node and the root node. The parent node is the direct parent node of the vertex. So for example, in the diagram below, the parent node of vertex 3 is 1, the parent node of vertex 2 is 0, and the parent node of vertex 9 is 9. And as for root node, it is a node without a parent node, and it can be viewed as the parent node of itself. So we can also think of it as an ancestor node. So for example, in the diagram below, the root node of vertices 3 and 2 is 0, and as for 0, it is its own root node and parent node, and likewise the root node and parent node of vertex 9 is 9 itself. Let's think about this question. Given a graph with certain vertices connected, how do we check if two vertices are connected? For example, we want to check if node 3 and node 0 are connected. Even though they are indirectly connected, they are still connected. By connection, it could be a direct one or an indirect one. How about nodes 2 and 8? Are they connected? The answer is no. How about 5 and 7? They must be connected, right? These are not hard to tell by just looking at the graph, but when there are thousands of vertices, you won't be able to tell by just looking at the graph. In that scenario, we will need help from the computers. So how can we solve this? We will need the help of disjoint sets. Let's look at how it works. Initially, we have 10 vertices labeled from 0 to 9. We want them to be independent and isolated. The first thing we need to do is connect the vertices. Let's connect 0 and 1 or make them a union and save them into a set. We have to do something rare, which is to choose a vertex as the root of the set. We can either choose 0 or 1, it doesn't matter. Let's say we choose 0, meaning the root of the set is 0. Now we will connect nodes 0 and 2. 0 is already in the set on the left, but 2 is independent by itself. We're going to connect 0 and 2, so we are going to add 2 to the set, and this is what happens. Now, if we check the root of nodes, we will find that the root of node 1 is 0, and root of node 2 is also 0, because they are both in the set, and both of their root is 0. Now let's connect 1 and 3. Since 1 is in the set on the left side, all we have to do is add node 3 to the set, which increases the size of the set. Now when we try to find the root of node 3, it will again be node 0. Now let's connect node 4 and 8. Node 4 is isolated and 8 is also isolated, so we can simply merge them into the same set. Since we just created a new set, we will need to find another root for the set. Let's choose 4 as the root. Next, we are going to connect 5 and 6. Since 5 and 6 has not been previously connected, we have to create a new set. Between 5 and 6, we have to choose a new root for the set. Let's choose 6. Next, we're going to connect 5 and 7. 5 is in the set with 6, so if we want to connect 7 with 5, we want to put 7 in that set that contains 6. At this time, if we want to find the root of 5, it is 6. And if we want to find the root of 7, it is also 6. For 8, the root is 4. If we want to find the root of 9, since it is an isolated node, the root of it is simply itself. We can say 9 is in a set by itself, so therefore the root of 9 is 9 itself. After the union operations, we have connected all the vertices. Now we are ready to check if the given two vertices are connected or not. In other words, we are checking if the two vertices are in the same set. For the first example, we have the nodes 0 and 3. For 0, the root of the set is 0. 3 is also in the set, so its root is 0 too. We realize that since they have the same root, they must be in the same set. Now let's look at 1 and 5. For 1, it is in the set, and its root is 0. For 5, its root is node 6. We see that 0 is not equal to 6. This means that they are not connected, which we can see as they are not in the same set. Next, let's look at 7 and 8. For 7, its root is 6, and for 8, its root is 4. We can see that 6 is not equal to 4, which means they are not in the same set. At this point, if we want to connect 0 and 5, 0 is in this set and 5 is in this set, making a union of 0 and 5, which means we're connecting the two sets together. Now we just have to merge the sets together to form a bigger set like this. We will also have to choose a root among all numbers in the set. For example, if we choose 0 as the new root, 6 will no longer be the root here. Let's look at 1 and 5 again. For 1, root is 0. For 5, now it is also 0. So they are not connected. As you can see, this is the basic idea of a disjoint set. I'm going to go over 2 ways to implement disjoint set in code, and I'll be using Python3. So the difference between these 2 ways are in the time complexity. The first one is path compression optimization. With that way, it will be O log n time and O n space. And with the second way, with path compression and union, it will be O amortized n time, which is regarded as constant time, O1, and space is also On. Obviously, the second one is better, but I want to slowly merge into the second one for better understanding of how we can implement. In this method, I'm going to use the path compression. So let's first define our union find. I'm just going to call it union find in this code because it's easier to type. Union find, define it as an object, and then we'll initialize it. It's going to take n, which is the size of the graph and size of how many vertices there are. And it's going to have a dictionary of parent. Each node's parent is going to be itself in the very beginning. And let's start our find function. Find, what find does is find returns the root, absolute root of that node. So it takes a node and then it will return its absolute root. So how can we do that? We want to, let me comment here, find the absolute root of a given node. So let's check our base case. So if node equals, here the parent, in what case would it be the absolute root, right? Remember when we did our example earlier, when 9 equals 9 itself, it is its absolute root. And that means when the node equals its own parent, it is an absolute root. So then we will return the node. And this would be our base case. And if not, we can just return the recursion self.find and then the self.parent node. This would recursively pass in the parent of that node. Let me comment this here so it's more clear. Keep looking for the node that points to itself. So that also means the parent of itself is itself, which makes it a root node. But look at this. This means this function, each time we pass in a node, it will keep recursively looking up until it finds its root node. Is that the most efficient way to write this using path compression? No, not necessarily, right? Because there's a better way we can do this to save us some time complexity. We can, instead of this, we can add a line here, self.parent node equals self.find self.parent node. And then instead of returning this here, we can return self.parent node. So this means using this way, we only need one operation, but in the process, we connected all of the nodes in this path directly to their root node instead of the original parent nodes. So then when we try to find one of these numbers the next time, we could go straight to the root node instead of searching step by step. So this really compresses our path. Let's move on to the union function. The union function will take in two nodes, right? Because we want to union them together. And first of all, we can find the root of the two nodes. If the node is already connected to a bigger component, we want to unionize them together, right? So let's find root 1 of node 1 would be self.find node 1, and then root 2 would equal self.find node 2. And then if we want to union these two nodes together, we can actually union these two roots together. And we can either combine root 2 to root 1, making root 1 the absolute root, or we can combine root 1 to root 2, making root 2 the absolute root. It doesn't really matter which one we do as long as we just combine them together. So in this case, we update it in our parent dictionary, so I'm going to update root 2 to root 1. Basically, this means now the final root is root 1, and we have unionized everything together. And we're done our union function. I'm going to write one final one called connected, where it returns true if two nodes are connected and returns false otherwise. It's going to take in node 1 and node 2. And yeah, so we just have to find if those two absolute roots equal each other, so we can use our find function. For node 1 equals self.find node 2, and if they equal true, if they do equal, it will return true, and otherwise it will return false. And then let's run an example to see if this works. I'll create an object first in our union find, and initialize this object to 10. Oh, is there something wrong here for I in range? Right. And uf.union. I can create a set of 0, 1, 2, and then another one of 3, 4, 5, 6, and another one with 7, 8, 9. Okay, this would be 10. And then I'll do uf.union 0 and 1. Okay, let's test this. uf.connected. Let's test 0 and 2. They should be in the same one. 0 and 2. This should return true. And let's do another true. So let's do 7 and 9. This should also return true. And let's do one false. Let's do 9 and 4. 4 and 9. This should be false. Let's run it and see. It says true, true, false, which is correct. This union find solution using path compression takes O log n time because of the recursion in the find function, and it takes O n of space by storing it in a parent dictionary. Now that we have completed our path compression solution, let's go over the amortized constant solution, which is path compression plus union by rank. Let me explain the concept of union by rank first. Let's say we have two trees here and we want to union 1 and 6. The first thing I'm going to do is find the root of node 1, which is 0. Then we're going to find the root of 6, which is 5. And then we're going to choose either node 0 or node 5 as our absolute root. I drew out the two scenarios. This tree is when 5 is chosen as the root node. What is the height of this tree? 1, 2, 3, 4, 5. This tree has height of 5. For this tree, I choose 0 as the root node. Its maximum height is 1, 2, 3, 4. The tree on the right side is shorter and thus more efficient. So how do we decide that 0 will be our root node? Now you see for these two trees, the tree on the left has height 1, 2, 3, 4. So 4. And the tree on the right is 2. If we choose 0 at this point as our root node, we can just connect 5 like this. So for this tree, its height doesn't change because we're just connecting a tree with a height of 2 to it. However, if we make 5 our absolute root and connect 0 to 5, at this point the height of the tree is already 4 because of node 0. By making 5 as the root node, the height of the tree now becomes 5. Thus, it made the tree taller. So what is the criteria to choose the root node? If we choose the root node of the taller tree as our new root node, in this case the tree that root 0 belongs to is taller. So we will add the shorter tree where node 5 is at to be the subtree of node 0 and choose node 0 as the absolute root. This way we can try to make the tree as balanced as possible instead of creating a tree like this. This is the concept of union by rank. We will make our decision based on the height of the tree. Whichever the tallest will dominate the rest and become the absolute root. So let's implement path compression plus union by rank in code. This will take amortized constant time. And space will still be on. Let's start. So first we'll also create the class object and we'll initialize it. It's gonna take self and n, which is the size of the graph. And we're gonna have a parent dictionary like we did earlier. And it's gonna be assigned to itself at first for I in range n, which is the size of the graph. And then we're also, this time because we want a rank of all the vertices, we'll create a rank. And we're gonna assign the rank to 1 in the beginning. And we're gonna times this by n, the size of the list. The size, how many vertices there are. Now let's write our find function. The find function actually doesn't change by adding this union by rank. The find will still be a recursion using path compression like we did earlier. So if node equals its parent, it means we found the absolute root and we can just return the node. And if not, we can recursively search for its parent's parent's parent until we reach the absolute root. And through this process, we repeatedly update each node to the root node on this path to the final absolute root. And we just have to return self.parent node. So this way we've utilized the path compression. And let's write our union function using union by rank. Again, it's going to take node 1 and node 2. And first, we're gonna get the root of two nodes, the node 1 and node 2. And we're going to compare it. If they do not equal each other, then we're gonna compare the rank of root 1 and root 2. So if self.rank root 1 is greater than self.rank root 2, this means root 1 is greater and we should merge root 2 into root 1. So we then change our parent of root 2 to equal root 1. And if self.rank root 1 is smaller than, let's do it the other way, root 2 is greater than self.rank root 1, then we do the opposite, right? We do self.parent root 1 equals root 2, we merge root 1 into root 2 instead, and else if the rank equal each other, that means we can either merge root 1 to root 2 or root 2 to root 1. It doesn't really matter which one we do, so I'm just gonna default this to parent. We're gonna just merge root 2 into root 1. And when we do that, we should also increase the rank of root 1. So that now it has a higher rank because we merged this to root 1. And I think this is all for the union by rank. So this is path compression and this is union by rank, and then let's just add our final function, connected. Connected will check if two nodes are connected. So it also takes a node 1 and a node 2, and it just returns true if node 1's absolute root equals node 2's absolute root. This should be everything for the best way to write union find, aka disjoint set. So this is actually using compression plus union by rank, path compression plus union by rank. The time of this is amortized constant, and the space is ON. This concludes my video on disjoint set, also known as union find. Please let me know if you have any questions in the comments, and thank you so much for watching.